In our previous lectures, we had discussed the response of high-pass RC circuit to the sinusoidal wave. As we know that if a sinusoidal wave is applied to a linear circuit, then the linear circuit does not change the shape of sinusoidal wave. It means that if a sine or cos wave is applied to a linear circuit, then output remains of the same shape. But now we are considering the case of non-sinusoidal voltage. We are applying a step voltage to the high-pass RC circuit, which is a linear circuit. Now in figure 2, there is shown the circuit of high-pass RC circuit. It is a combination of a capacitor and a resistor, and if an input voltage is applied to the circuit and the output is taken across the resistor, then it is called high pass RC circuit. And to this circuit, we are applying this step voltage, which is shown in figure 1 as the input voltage. Before discussing the details of this procedure, let us first discuss what is a step voltage. It is shown in this figure number 1. Step voltage means a voltage which is 0 for time less than the reference time. Suppose we represent the reference time as t equal to 0, then the voltage is perfectly 0 for time less than 0, and it suddenly rises. It abruptly rises at the reference time, that is t equal to 0. It abruptly rises, that is the rise is almost vertical, and after that it becomes V naught, and which remains constant forever, that is we can say it remains constant till infinity. So if this condition is satisfied, then the voltage is called step voltage, and this step voltage is applied as input voltage to the high pass RC circuit. Now we do not know the exact nature of the output voltage, though we exactly know what is the nature of input voltage. So we represent the input voltage at any time t as VIT. Though we know the exact nature of the input voltage, yet we have represented it by general expression VIT, and the output voltage we have represented as V naught T, which is a voltage at any general time T, and we have to find out the exact nature of V naught T. Now let us find out what is the output voltage at t equal to 0. That is, when the input voltage suddenly increases, it increases sharply from 0 to V naught. What is the output voltage at that time? Input voltage is increasing from 0 to V naught. What is the output voltage across the resistor? Now we know that when a applied voltage suddenly changes, then the voltage across the capacitor cannot change instantaneously, because the procedure of capacitor voltage is through charging and discharging. If the applied voltage changes abruptly and suddenly, then the voltage across the capacitor does not and cannot change instantaneously. It means that the voltage across the capacitor will remain zero. When the input voltage is sharply increasing, the voltage across the voltage or potential difference across the capacitor will remain zero. Therefore, the entire voltage increase which has happened at the input will appear across the output resistor. Or in other words, if the change in the input voltage is from 0, so we have deduced that the output voltage for t equal to 0 is equal to the applied maximum voltage, that is V naught. Now we have to find out what is the nature of the output voltage for t greater than 0. As the capacitor is connected in the circuit, therefore we can presume that the output voltage is in the form of exponential variation, because whenever the capacitor is present in a circuit, then the charging and discharging of the capacitor is in the exponential manner. Suppose that the nature of output voltage is given by equation 1, where V naught T we have assumed as the output voltage at any time t. It is of the form B1 plus B2 e raised to the power minus t upon tau, where B1 and B2 are constant unknown quantities and, sorry, and tau is the time constant of the RC circuit. Therefore, the time constant tau is equal to R multiplied by C. Now we have to calculate the values of B1 and B2, which are constant and unknown quantities. And to find the values of B1 and B2, we have to make use of whatever information we have got about the RC circuit and the case of a step voltage applied to the input. The first thing, we know that when t is equal to infinite or it is infinity, then the output voltage will reach the final value, because when time is infinite, then the output voltage is has attained its final value, and suppose it is Vf. Therefore, Vf, output is Vf, is equal to B1 plus B2 into e raised to the power infinity, because t is infinity. Now e raised to the power minus infinity, this term will become 0. Hence, B1 is equal to Vf. Hence, this constant quantity B1 is equal to the final voltage, that is Vf. Hence, equation number 1 becomes V naught t is equal to Vf plus B2 e raised to the power minus t upon tau. Now the second point is, when t is equal to 0, the output voltage is equal to the input voltage, because the initial condition, the input voltage is Vi. So Vi is equal to Vf. Since B1 is Vf, it is Vf plus B2 e raised to the power minus 0. And e raised to the power 0 or minus 0 is equal to 1. Hence this equation becomes Vi is equal to Vf plus B2, or the constant B2 is equal to Vi minus Vf. Hence the expression for the output voltage becomes Vf, since B1 is Vf plus B2 is Vi minus Vf into e raised to the power minus t upon tau. This is the general expression for the output voltage of the high pass RC circuit when step input voltage is applied to this circuit. Now let us put the values of Vi and Vf in the above equation. As we have discussed in the earlier slides, the initial value of output voltage is, which we have represented as Vi, is equal to V naught. We have discussed it earlier that at time t equal to 0, the output voltage is equal to the maximum applied voltage at the input, and we have to see what is the final value of and we have to see what is the final value of output voltage. And we know that after time t equal to 0, that is for time t greater than 0, the input voltage becomes perfectly constant. In the circuit, the input voltage or applied voltage becomes absolutely constant for t greater than 0. And whenever there is a capacitor in the circuit, it ultimately blocks the constant voltage. Hence, we can say that the role of capacitor is to finally block the input constant voltage, because initially it is behaving as a short circuit because it is passing all the applied voltage to the output. Hence at t equal to 0 it is v naught, but finally the role of capacitor comes into play, and the capacitor blocks the constant voltage which is being applied. Therefore the final output voltage will be 0. Therefore vi is equal to v naught and vf is equal to 0. Therefore the general expression for the output voltage is equal to v naught into e raised to the power minus t upon tau. By mistake, this term which should be V naught here, it is misprinted or it is mistyped here. So at this point, it should be V naught instead of V. And if we suppose x is equal to t upon tau, then this equation becomes V naught t upon V naught is equal to e raised to the power minus x. So if we draw the the variation of this output voltage or V naught t upon V naught with respect to x, then it is in the form of exponential curve like this. So the input voltage was in the form of a step voltage. It was like this is the input voltage, and the output voltage is like this. Hence at the input of the high pass RC circuit, we had applied the step input voltage, and at the output we are getting a wave which is of this form. So in the earlier slide we have discussed that if the input voltage applied to the high pass RC circuit is in the form of step voltage, it is like this. At time t equal to 0, it suddenly rises, and after that it becomes constant forever. Then the output voltage will be in the form of exponential wave. That is, at t equal to 0, it will be maximum, and after that the output voltage will start decreasing in the exponential manner. Now there is a term called fall time in whole of this episode, and the fall time gives an idea how fast the output voltage is falling with the increase in time. That is, it shows the exact nature of the output voltage. The fall time is technically defined as the time taken by the output voltage to fall from 90% of its maximum initial value to 10% of its maximum value. And in the graph it is shown as time t1 and t2. From 90% to 10% of the maximum value, the time taken by the wave to decrease from 90% to 10%. So we have shown it mathematically.
if we put the value of 90% of output voltage and 10% of the output voltage in equation in the previous slide, then we can get time t1, that is the time at which the output voltage is 90%. It comes out to be approximately equal to 0.1 of time constant tau or RC. And for the time t2, the time at which the output voltage remains 10% of the maximum value, then it comes out to be T2 is equal to 2.3 times tau, that is RC, and the difference between these two, which we have defined as the fall time, it is equal to 2.3 minus zero point 0.1 times tau, or it is equal to 2.2 into time constant. So this is the expression for the fall time of high pass RC circuit. Now, as discussed earlier, the lower cutoff frequency of high pass RC circuit. When a wave is applied to the high pass RC circuit and we are uh, using the sinusoidal wave, then there is a term called lower cutoff frequency. The frequency at which the output voltage is 70.7% of the maximum value, and that lower cutoff frequency is expressed as 1 upon 2 pi RC or 1 upon 2 pi tau. This is a property or characteristic of high pass RC circuit, and this term depends upon the constant values of the resistance and the value of capacitance. So this lower cutoff frequency is an inherent characteristic property of the high pass RC circuit. And from this equation we can say that the time constant tau is equal to 1 upon 2 pi f1, where f1 is the lower cutoff frequency. So we can, from this equation, we can find out the relationship between the fall time and the lower cutoff frequency by combining equation number this expression for the fall time and the expression for tau, and it comes out to be TF, that is fall time, is equal to 0.35 divided by F1, or in other words we can say that the fall time is inversely proportional to the lower cutoff